This last video will cover an application of the dot product, specifically the idea of work, which in the context of physics has the specific meaning in that it describes what is accomplished by the action of a force when acting on an object over some distance. So if you have a force acting on an object over a given distance, that's when work has been accomplished in a technical sense. And I'm going to skip this sort of mathematical definition and go just to the example. We'll come back to the formula. And to give you an illustration of this, I think it's best described with an illustration. So the situation we're given is that there's a really heavy barn door that we need to close. Well, we could draw the barn, but there's the door. Here's the sort of doorway, and we're trying to move this door. I guess I'll try to move this door this way. But we've just got this rope to sort of help us do that. Okay, there's our little farmer moving the door. And okay, just to kind of give this a little bit of more, make this a little more mathematical here, make this easier to talk about, what we're going to do is we're going to move this point, which I can call P, over to this point Q. Okay? And that actually, we can think of that as a vector. That would be technically a displacement vector. It shows the displacement of the door from point P to point Q. I'm going to make that, I'm going to give that a different color here. How about yellow? So vector PQ is the displacement vector. And if you read the problem, it says, to close a sliding door, a person pulls on a rope with a constant force of 50 pounds. That's one of the units for forces, pounds, at a constant angle of 60 degrees. Find the work done in moving the door 12 feet to its closed position. So, in other words, this displacement vector, PQ, has a magnitude of 12 feet. That's the distance that we've got to move the door. And technically, in terms of, the P and Q here, that's the magnitude of our vector PQ, the magnitude of the displacement vector. Okay. Well, I didn't mean to draw that on there. Well. Go to my eraser. There we go. Okay. Now it says that the farmer is pulling on the door with a rope, and he's pulling on the rope with a force, and the force itself can be represented as a vector because it has a magnitude and a direction, right? It matters what direction he's pulling on the door with. If you've ever pulled on something like this, you know that if you were standing up here and pulling, if you were, like if the farmer was higher up, or let's say this, maybe I'll describe it this way. That it tells us the angle between the door and the rope is 60 degrees. So this theta is 60 degrees. If the angle was less, if he was like a lot taller and the angle was 10 degrees, you could see that with the same force he could pull, he could do a lot more work on the door. It'd be a lot easier to pull. If the farmer had walked closer to the door, and so the angle was greater that he was pulling on. If it was more like there's the displacement vector, here's the force vector. If he's pulling like that, not much work is going to get done on the door. It's very hard to pull like that. If he was if this is the displacement vector and he's pulling on the door with the force vector like that with a very small angle here, now his force is going to accomplish a lot of work. It would be easier to move the door. And the reason is because not all of the force is being used to move the door, right? The only part of the force that is being used to move the door is the part of the force that's going in the same direction as the displacement vector. In other words, if I break the force vector down into two components, the only part of the force that's doing work is this orange part. Well, the other part's orange too, but the not dotted part. That part of the force, the horizontal part in this case, is the only part of the force that's doing work to move the door. So the way that we define that work is defined is as the part of the force vector the magnitude of the part of the force vector going in the same direction as the displacement vector times the magnitude of the displacement vector. If you remember from the second video, that is the definition of a dot product. That's what a dot product is. So the work being done is just the dot product of the force vector times the displacement vector, which they're going to, in this case, they'll call PQ. Because again, it's only the orange part of the force that's being used to move the door, because it's going in the same direction as the displacement. This dotted line, this part of the force doesn't count. That's why if you were standing here moving, you'd have a smaller part of your force being used to move the door, and if you were standing here moving it, you'd have a much larger part of your force being used to move the door. Okay. Now we could if we're given the two vectors in component form, that formula is useful, and that's what they give us up here. F dot PQ. That's the technical definition of work, the force vector dot product with the displacement vector. But in this case, we're given actually the magnitude of the displacement vector. We're given also the magnitude of the force. They told us the magnitude of the force, I'll write this down here, was 60 pounds. And they gave us the angle between the two. So in this case, it's actually more useful to use the alternate definition of a dot product. If you remember from the other video, U dot V equals the magnitude of U times the magnitude of V times cosine of the angle. Do you remember that? Let's see. I'll write it down just in case we forgot. U dot V equals magnitude of U. Oh, that's pretty sloppy. Magnitude of U. Magnitude of V cosine theta. Well, it applies in this case as well. F dot PQ is just going to be the magnitude of F times the magnitude of PQ times cosine theta. That's a formula that we can use for work. And here we're given the magnitude of F, it's 60 pounds. We're given the magnitude of PQ, it's 12 feet. And we're given the angle, so times cosine theta. Or cosine, 60. I got a little messy there, but it's 60 pounds times 12 feet times cosine of 60. Put this into your calculator, or really, you don't even need to put this into your calculator because cosine of 60 is a half. We should always kind of take opportunities to keep the unit circle fresh in our mind, right? Cosine of 60 is a half. We have a half times 12 times 60. So that's 60 times 6. That's 360. And then pounds times feet, we're going to call those foot pounds. That's 1 unit for work. It's moving. It's the equivalent of moving 360 pounds 1 foot, or moving 1 pound 360 feet. That amount of work is the amount of work this guy just did. One more thing before I let you go. You notice here this definition given for work, or first of all, work is a scalar. Work has no direction, right? No direction, just magnitude. It's a scalar. Also, this definition they give you, the projection of F onto PQ times the magnitude of PQ. That's just another way of writing what I wrote. In other words, this part is, oh, I'm sorry, you know what? This part, magnitude of the force times cosine theta. If you take those two together, that is the orange part here, which is the projection of F onto PQ, if you think about it on the previous video when we talked about projections. Okay, so a lot of the notation is kind of new and perhaps intimidating. Some of these diagrams, hopefully they were clear. Maybe they get a little abstract, but you can always watch the video again. But really the calculation, once you've set it up in the calculation, was extremely simple, right? All right, that'll be all, and I'll see you guys on Monday.